Look up at the night sky on a clear evening, and you'll see stars, planets, and maybe even a faint streak of the Milky Way. But what if I told you some of those distant galaxies shimmering in the darkness aren't actually where they appear to be? What if the universe itself is playing tricks on us, bending light like a funhouse mirror to create illusions so convincing they've fooled even the most advanced telescopes? This isn't science fiction, it's the cosmic mirage, one of space's most mesmerizing phenomena, where gravity twists the fabric of reality, warping light into ghostly duplicates, stretched arcs, and rings of fire that shouldn't exist. And here's the wildest part. These celestial illusions aren't just curiosities. They're the universe's way of whispering its deepest secrets to us, revealing the invisible scaffolding of dark matter and the true shape of space-time itself. Think about the last time you saw a mirage on a hot road, the way the air shimmers, making puddles appear where there's only asphalt. Now picture that same trick happening on a cosmic scale, with entire galaxies acting as the heat haze and the gravitational pull of invisible matter as the distorting force. Over a century ago, Einstein predicted this very effect, arguing that massive objects could bend light like a lens, but even he might have been stunned to see just how far that idea would take us. Today, astronomers use these cosmic mirages like breadcrumbs, tracing the contours of the unseen universe. Every distorted image, every stretched streak of starlight, is a clue, a puzzle piece in a grander mystery about how space, time, and gravity intertwine. So how do we decode these illusions, and what can they teach us about the universe's hidden architecture? From the first blurry photographs of twin quasars that turned out to be the same object, to the breathtaking rings of light captured by modern observatories, we're about to embark on a journey where nothing is quite as it seems. We'll unravel how scientists turn these cosmic tricks into a roadmap of the invisible, probing the gaps in our knowledge where dark matter lurks and gravity defies expectations. By the end, you'll never look at the night sky the same way again, because once you understand the cosmic mirage, you'll realize the universe isn't just showing us its wonders. It's hiding them in plain sight. Light behaves differently in the depths of space than it does here on Earth. Out there, where gravity reigns supreme, even something as seemingly straightforward as a beam of light doesn't follow the rules we're used to. Picture a marble rolling across a stretched bedsheet. The heavier the object pressing down on the fabric, the more the marble's path curves. Now replace the marble with a photon of light, and the bedsheet with the very fabric of space-time itself. That's gravitational lensing in action. When light from a distant star or galaxy travels past a massive object like a cluster of galaxies or a black hole, it doesn't just zip by in a straight line. Instead, the crushing gravity of that object warps space around it, bending the light's trajectory like a cosmic detour. Sometimes, this bending creates multiple images of the same object, as if the universe hit copy-paste on a galaxy. Other times, the light gets stretched into a glowing arc or even a perfect ring, a phenomenon called an Einstein ring, named after the scientist who first predicted it. But these aren't just celestial oddities, they're tools. Astronomers use these distorted images like cosmic scales, measuring how much mass it takes to bend light that dramatically. And here's where it gets really interesting often. The amount of bending doesn't match the visible matter in a galaxy. There's something extra there, something invisible tugging at the light. That's something dark matter. By analyzing these light-bending effects, scientists can map out where dark matter lurks, tracing its hidden influence across the cosmos. It's like using a flashlight to cast shadows in a dark room, except instead of furniture, we're revealing the invisible scaffolding of the universe. And the more we study these cosmic mirages, the more we realize just how much of reality is shaped by forces we can't even see. From confirming Einstein's theories to uncovering the fingerprints of dark matter, the way light twists through space isn't just a curiosity, it's a roadmap to the universe's deepest mysteries. Einstein's genius wasn't just in solving equations, it was in seeing the universe as a living, breathing entity where space and time dance together. When he first proposed that massive objects could bend light, many dismissed it as pure theory, too strange to be real. But in May 1919, during a total solar eclipse, astronomers finally had their proof. As the moon blocked the sun's blinding light, stars near the sun's edge appeared slightly out of place, just as Einstein's calculations had predicted. The fabric of space itself had warped, tugging their light off course. Overnight, the world realized gravity wasn't just a force, it was the curvature of spacetime itself, and light was its obedient traveler. This revelation didn't just make Einstein famous, it rewrote the rules of astrophysics. Suddenly, the cosmos wasn't a static backdrop dotted with stars, but a dynamic stage where matter and energy mold the very geometry of reality. And the most astonishing part, Einstein himself doubted we'd ever see the full extent of his idea in action. He thought the effect would be too subtle to detect beyond our solar system. Yet here we are, a century later, watching galaxies act as colossal lenses, magnifying and distorting light from objects billions of light years away. These cosmic mirages aren't just confirming his theory, they're pushing it further, revealing gaps in our understanding that even Einstein couldn't foresee. Take the case of the Einstein cross, a quasar so perfectly aligned behind a distant galaxy that its light splits into 4 mirror images, arranged like petals around the lensing galaxy's core. Or the cosmic horseshoe, a galaxy stretched into a near-perfect ring by the gravity of a foreground cluster. These aren't just pretty pictures, they're cosmic scales, letting astronomers weigh the unseen. When the amount of bending doesn't match the visible mass, it's a smoking gun for dark matter's presence. Einstein gave us the math, but the universe handed us the evidence, proving that the deepest truths often hide in the warped reflections of distant starlight. What's even wilder, gravitational lensing isn't just a tool for observing the universe, it's a time machine. When light bends around a massive object, it takes different paths to reach us, some longer than others. That means we might see multiple versions of the same supernova, flickering to life years apart like a cosmic echo. It's as if the universe is replaying its greatest hits, giving us front-row seats to events that should have been lost to time. From testing relativity to mapping the invisible, Einstein's impossible prediction has become astronomy's most versatile tool, turning the cosmos into a hall of mirrors where every reflection holds a secret. The cosmos doesn't just bend light in one way, it twists it into a gallery of illusions, each with its own story to tell. Take strong gravitational lensing, the universe's most dramatic sleight of hand. When a distant galaxy aligns perfectly behind a massive foreground cluster, the result isn't just a bend, it's a full circle spectacle, an Einstein ring. These radiant halos aren't just rare cosmic bullseyes, they're precision instruments. The symmetry of the ring reveals the mass of the lensing galaxy down to the last invisible wisp of dark matter, like measuring the weight of a shadow. But not all lensing shouts its presence. Weak lensing works in whispers, subtly warping the shapes of thousands of background galaxies like a hall of mirrors at a funfair. Alone, each distortion is barely noticeable, but collectively, they paint a panorama of the universe's hidden scaffolding. Astronomers analyze these gentle bends like forensic scientists studying fingerprints, reconstructing the distribution of dark matter across vast cosmic voids and filaments. It's how we've mapped the universe's large-scale structure, not by seeing the invisible, but by reading the wrinkles it leaves in starlight. Then there's microlensing, the universe's fleeting magic trick. Here, a single star temporarily brightens when an unseen object, a rogue planet, a neutron star, even a solitary black hole drifts in front of it, magnifying its light like a cosmic magnifying glass. These events last days or weeks, vanishing as quickly as they appear, but in that brief window, they unveil celestial nomads otherwise lost in the darkness. Microlensing doesn't just find hidden objects, it senses the loners of the galaxy, the cosmic drifters that slip through every other net. Together, these mirages form a toolkit as versatile as it is unexpected. Strong lensing cracks open the secrets of galaxy clusters. Weak lensing traces the ghostly outlines of dark matter. Microlensing spots the wanderers invisible to telescopes. And sometimes they overlap like the bullet cluster, where weak lensing revealed dark matter's eerie separation from visible gas after a galactic collision, while strong lensing pinpointed the precise mass of the wreckage. The universe's illusions aren't just quirks, they're its way of turning every distortion into a clue, every bend into a measurement. And with each one, we're not just seeing the cosmos, we're decoding its hidden blueprints. When the Hubble Space Telescope first turned its unblinking eye toward the cosmos, it didn't just capture pretty pictures, it rewrote the rules of what we thought was possible. Among its most breathtaking discoveries are the warped galaxies and luminous arcs that reveal gravity's invisible hand at work. Take the space arc in Able 3708, a galaxy cluster so massive it bends light like a prism, smearing a background galaxy into a glowing crescent that defies logic. Or the Ghost Galaxy, a delicate ring of stars stretched into a perfect Einstein ring by the gravitational pull of an unseen neighbor. These aren't just celestial curiosities, they're Hubble's way of turning the universe into a laboratory. Hubble's precision is unmatched. While ground-based telescopes struggle with Earth's turbulent atmosphere, Hubble orbits above the distortion, capturing gravitational lenses with crystal clarity. This sharp vision lets astronomers do something extraordinary: use bent light as a cosmic tape measure. By analyzing how much a galaxy's image stretches, they can calculate the mass of the lensing object, including the dark matter that leaves no other trace. Hubble's observations of clusters like Able 1689 revealed dark matter's spiderweb structure, mapping its invisible strands across millions of light years. But Hubble's greatest trick, turning gravity into a time machine. In the famous ultra-deep field image, a single patch of sky smaller than a grain of sand held at arm's length reveals thousands of galaxies, many magnified and twisted by foreground clusters. These lensed galaxies aren't just farther away, they're snapshots of the universe in its infancy. By studying their warped light, we've glimpsed galaxies born just 400 million years after the Big Bang, their light bent and amplified by cosmic lenses Hubble helped decode. The telescope's legacy goes beyond stunning imagery. It settled one of astronomy's fiercest debates by measuring the Hubble constant, the rate of the universe's expansion, using lensed quasars as mile markers. And when its data revealed discrepancies in that expansion rate, it didn't mean failure. It uncovered a new mystery, hinting at unknown physics lurking in the cosmic shadows. From confirming Einstein's wildest predictions to exposing the gaps in our understanding, Hubble didn't just observe gravitational lensing. It turned it into a language, one that speaks volumes about the universe's hidden architecture. Every distorted galaxy it captured is a testament to how far we've come, and a reminder of how much we've yet to learn. Dark matter is the universe's silent architect, shaping everything we see while remaining utterly invisible. Imagine building a house where the scaffolding vanishes once the walls are up. Dark matter works the same way, holding galaxies together without leaving a trace. When light bends around a galaxy cluster, the amount of distortion often exceeds what the visible stars and gas can explain. That extra tug, that's dark matter's fingerprint. It's gravity warping space like an unseen hand pressing down on cosmic fabric. One of the most striking examples is the Bullet Cluster, where two galaxy clusters collided in a cosmic wreck. The visible gas, hot and glowing, slowed down like cars in a traffic jam, but the dark matter detected only by its lensing effect sailed right through, leaving the stars and gas behind. This wasn't just proof dark matter exists. It showed how it behaves ghostly and indifferent to the collisions of ordinary matter. Without dark matter's gravitational glue, galaxies would fly apart, their stars scattering like marbles dropped on a trampoline. Yet for all its influence, dark matter remains maddeningly elusive. It doesn't absorb, emit, or reflect light, hence the name. But gravitational lensing gives us a way to see it. By mapping how light bends around galaxy clusters, astronomers create detailed charts of dark matter's distribution, revealing vast halos around galaxies and sprawling filaments connecting them like cosmic spiderwebs. These maps show dark matter isn't just sprinkled randomly. It forms an intricate skeleton, a hidden framework that guides where galaxies form and how they evolve. The real puzzle, we still don't know what dark matter actually is. Is it a sea of undiscovered particles, colder than the void of space, or something even stranger, defying the laws we know? Lensing observations have ruled out some theories while deepening the mystery of others. For instance, certain small-scale lensing patterns suggest dark matter might be clumpier than expected, hinting at unknown physics at work. Every distorted galaxy, every stretched arc of light, is another piece of the puzzle, a clue whispered across billions of light years. What's clear is that dark matter isn't just a cosmic placeholder. It's the force that sculpted the universe, pulling ordinary matter into galaxies and clusters while remaining forever in the shadows. And thanks to gravitational lensing, we're finally starting to trace its outline, like feeling the shape of an object in the dark. The more we study these cosmic mirages, the closer we get to answering one of science's biggest questions. What is the universe really made of? Until then, dark matter remains the ultimate ghost in the machine, invisible yet indispensable, bending light to remind us how much we have yet to discover. If dark matter is the universe's invisible glue, dark energy is its mysterious counterforce, an enigmatic push that's stretching the cosmos apart at an ever-increasing speed. Picture a balloon inflating faster and faster, not because someone's blowing into it, but because the rubber itself is somehow generating its own expansion. That's the unsettling reality astronomers faced in the late 1990s when they studied distant supernova, expecting to find the universe's expansion slowing down under gravity's pull. Instead, they discovered the opposite. Galaxies were racing away from each other faster as time went on, as if some unseen hand had pressed the cosmic accelerator. This discovery upended everything. For decades, scientists assumed gravity would eventually reign in the universe's expansion, maybe even reverse it in a big crunch. But dark energy flipped the script, revealing a cosmos where space itself seems to generate repulsive energy, overpowering even dark matter's grip. And here's where gravitational lensing becomes a critical tool in this cosmic detective story. By measuring how light bends around galaxy clusters at different distances, and thus different epochs in cosmic history, astronomers can track how dark energy's influence has changed over billions of years. It's like reading the universe's diary, with each warped galaxy acting as an entry that reveals how hard dark energy has been pushing at that moment in time. Some theories suggest dark energy isn't just a constant force but something that evolves, growing stronger or weaker as the universe ages. If that's true, gravitational lensing might hold the key to spotting those subtle shifts. Imagine a lensing effect that's slightly stronger or weaker than expected for a galaxy cluster's mass. That discrepancy could hint at dark energy's changing influence, tweaking the very fabric of space-time in ways we're only beginning to grasp. The Euclid Space Telescope, launched in 2023, is designed to hunt for these exact clues, mapping billions of galaxies to measure how lensing patterns vary across cosmic time. But the biggest question remains: what is dark energy? Is it the cosmological constant Einstein once proposed, a static energy woven into space itself? Or is it something far stranger, like a dynamic field that fluctuates, or even a sign that our understanding of gravity is incomplete? The answers could determine the universe's ultimate fate. If dark energy keeps strengthening, it might tear galaxies apart in a big rip. If it weakens, gravity could regain the upper hand, pulling everything back together. Right now, we're caught in a cosmic tug of war between these two invisible giants, and gravitational lensing is one of the few tools sharp enough to trace their battlefield. Every distorted galaxy, every stretched arc of light, isn't just a snapshot of the universe's hidden structure. It's a timestamp in a grand experiment, one that's testing whether the cosmos will fade into cold emptiness or collapse into a fiery rebirth. And with each new observation, we're not just solving a puzzle, we're rewriting the story of everything. One of the most mind-bending aspects of cosmic mirages isn't just what they show us, it's when they show us. Light doesn't travel instantaneously. It ambles across the universe at a leisurely 300,000 kilometers per second. That means every beam of starlight reaching us is a postcard from the past, and gravitational lensing cranks this effect up to 11. When a distant galaxy's light gets bent around a massive foreground cluster, it doesn't just take one path, it snakes along multiple routes, each with a different travel time. The result: we might see the same galaxy at 3, 4, even 5 different stages of its life, all in a single frame. It's like stumbling upon a family photo album where the same person appears as a newborn, a teenager, and an adult, all on the same page. Take the supernova Revstal, a stellar explosion whose light was split and delayed by a lensing galaxy cluster. Astronomers first spotted one image of the blast in 2014. Then, thanks to light taking a longer path, watched the same supernova reappear in a different part of the cluster a full year later. This wasn't just a cosmic rerun. It was a rare chance to study a single cataclysmic event from multiple angles in time, like rewinding and replaying a movie scene frame by frame. These time-staggered images let scientists test how supernovae evolve, refining our understanding of how stars live and die. But the real power of these cosmic time machines lies in their ability to magnify the faintest whispers of the early universe. Normally, galaxies from the cosmic dawn, those born just a few 100 million years after the Big Bang, are too distant and dim to study in detail. Yet when lensing stretches and brightens their light, suddenly we're peering into nurseries where the first stars were forged. In one celebrated case, a lensed galaxy nicknamed the Sunburst Arc revealed clusters of young stars so dense and bright, they acted like cosmic flashlights, ionizing the primordial fog of the early universe. Without lensing, these details would have been lost in the glare of time. And here's the kicker: because lensing preserves light from different epochs, astronomers can literally compare a galaxy's youthful phase to its mature self within the same observation. Imagine watching a time lapse of a sapling growing into a towering oak, but instead of decades, it's compressed into a single Hubble image. These snapshots have exposed how galaxies bulk up, not just by gobbling gas, but by merging with neighbors in violent collisions that trigger bursts of star formation. They've even caught supermassive black holes in their awkward teenage years, gorging on matter and belching out jets of energy that shape their surroundings. The universe didn't just give us a telescope, it handed us a time machine with a zoom lens. Every warped image, every delayed flash of light, is a window into cosmic history, letting us witness the transformations that shaped everything from the tiniest stars to the largest galaxies. And as our telescopes grow sharper, these mirages will keep revealing chapters of the universe's story we've only dreamed of reading until now. Of all the cosmic mirages, Einstein rings stand out as nature's most breathtaking optical illusions, flawless circles of light etched across the universe like celestial wedding bands. These perfect rings don't form by chance. They require an almost impossible alignment. A distant galaxy must sit directly behind a massive foreground object, its light bent so evenly around the lens that it wraps into a complete halo. The odds of such precision are astronomically low, making each ring a rare glimpse into gravity's most elegant performance. What makes these rings so valuable to scientists? It's their symmetry. Unlike distorted arcs or smeared galaxies, an Einstein ring's perfect curve acts like a cosmic scale, revealing the exact mass of the lensing object down to the smallest detail. Every subtle kink or ripple in the ring's brightness traces the hidden distribution of dark matter, mapping its invisible grip on spacetime. Take the Molten Ring, a lensed galaxy discovered by Hubble in the constellation Fornax. Its luminous circle isn't just pretty, it's a forensic snapshot, showing how dark matter clumps around the foreground galaxy like an unseen shadow. But the real magic happens when these rings magnify the distant universe. In 2020, astronomers spotted an Einstein ring nicknamed the Cosmic Horseshoe, where the lensed galaxy's spiral arms were stretched into a fiery loop. Normally, such fine details would be lost across billions of light years, but the ring's magnification acted like a universal zoom lens, exposing pockets of star formation and even individual stellar nurseries. It's as if the universe handed us a microscope tuned to the most distant corners of existence. The most astonishing part, Einstein himself thought these rings would remain theoretical. When he first calculated the effect in 1936, he dismissed the idea as unobservable, writing that there was no hope of seeing such a phenomenon. Yet today, thanks to telescopes like Hubble and the James Webb Space Telescope, we've catalogued dozens of these rings, each one a silent rebuke to Einstein's skepticism. Some, like the Canaria's Einstein ring, are so pristine they could have been drawn with a compass, their geometry so precise they've become laboratories for testing relativity itself. And the discoveries keep coming. Recently, the James Webb Telescope captured an Einstein ring so distant, the lensed galaxy's light dates back to when the universe was just 2 billion years old. By analyzing its warped glow, researchers found something unexpected. The young galaxy was forming stars at a rate 50 times faster than the Milky Way, a frenzy of creation frozen in time by gravity's lens. Rings like these aren't just cosmic curiosities, they're time capsules preserving moments from the universe's adolescence that we'd otherwise never witness. From confirming the bedrock rules of gravity to exposing the violent stellar factories of the early cosmos, Einstein rings are more than just pretty circles in the sky. They're proof that even a century after their prediction, the universe still has ways of surprising us, turning what seemed like mathematical abstractions into dazzling, unignorable truths. And with every new ring discovered, we're reminded, sometimes the most profound secrets hide in the simplest shapes. The future of gravitational lensing isn't just bright, it's revolutionary, with next-generation telescopes poised to turn the cosmos into an open book. Take the James Webb Space Telescope, with its infrared vision slicing through cosmic dust like a warm knife through butter. While Hubble gave us breathtaking lensed galaxies, Webb goes further, capturing light from the universe's first stellar nurseries, objects so ancient their light has been stretched into the infrared by the expansion of space itself. Imagine studying a newborn galaxy magnified by a foreground cluster, its delicate tendrils of gas and fledgling stars visible in unprecedented detail. Webb isn't just observing these lensed relics, it's dissecting them, revealing the chemistry of the early universe and how the first seeds of structure took hold. Then there's the Vera C. Rubin Observatory, a ground-based behemoth with a camera so wide it could capture 40 full moons in a single shot. Every few nights, Rubin will scan the entire southern sky, cataloging millions of gravitational lenses in what amounts to the largest cosmic census ever attempted. This isn't just about quantity, it's about patterns. By comparing subtle distortions across countless galaxies, Rubin could uncover anomalies in gravity's behavior, testing whether Einstein's theory holds true on the largest scales or if dark energy's push is changing over time. Picture a map of the universe where every ripple in starlight flags an unseen mass, rogue black holes, orphan planets, or even exotic particles streaming through space. But the real game changer lies in the synergy between these tools. Webb's precision and Rubin's breadth will work in tandem, like a microscope and a wide-angle lens. While Webb zooms in on individual lensed quasars to measure the universe's expansion rate, Rubin's big data approach will spot statistical oddities, clusters where the lensing is too strong, or galaxies that seem to float in voids too empty. These discrepancies could hint at entirely new physics, from fuzzy, dark matter to extra dimensions warping spacetime in ways we've yet to imagine. And let's not forget the wildcard technosignatures. If an advanced civilization built a Dyson swarm around a star, the megastructure's irregular shape might subtly alter the light bending around a foreground galaxy. Far-fetched, maybe, but with telescopes now scanning millions of lenses, even the slimmest chance becomes a thrilling possibility. From probing the universe's first moments to hunting for cosmic engineers, the next decade of lensing studies won't just fill textbooks, it could rewrite them. The cosmic mirage, once a curiosity, is becoming our sharpest tool for decoding the universe's greatest mysteries. And with every new lens discovered, we're not just seeing farther, we're seeing deeper into the hidden layers of reality itself. Gravitational lensing might seem like just another optical illusion at first glance. After all, both play tricks on our perception by bending light, but the similarities end there. A desert mirage shimmers because hot air near the ground bends sunlight unevenly, creating the illusion of water where none exists. It's a local quirk, a fleeting trick of the atmosphere. Cosmic mirages, on the other hand, are etched into the fabric of reality itself. When light curves around a galaxy or black hole, it's not passing through layers of heated air. It's navigating the warped geometry of space-time, a distortion caused by sheer mass. Think of it like the difference between a funhouse mirror and a blacksmith's anvil. The mirror bends your reflection temporarily, but the anvil reshapes metal permanently under immense force. Gravitational lensing does the latter to light, molding its path with the unyielding weight of entire galaxies. And unlike earthly illusions, which fade with a change in perspective, cosmic mirages are locked into the universe's structure. They're not glitches, they're features written into the laws of physics. This distinction matters because gravitational lensing isn't just a curiosity, it's a diagnostic tool. While a desert mirage tells us about air temperature, A lensed galaxy reveals the mass of everything in its path: visible stars, hidden dark matter, even the invisible tendrils of cosmic filaments. Take the famous Cheshire Cat galaxy group, where the smiling arcs of lensed light aren't just whimsical shapes. They're precise measurements, showing astronomers that most of the system's mass lurks not in the glowing eyes of the foreground galaxies, but in the faint grin of dark matter between them. What's truly remarkable is how lensing turns distortion into data. On Earth, optical illusions are flaws to be corrected. A bent straw in a glass of water is just a trick of refraction. In space, a bent galaxy is a roadmap. The amount of stretching, the angle of the arc, even the time delay between multiple images of the same supernova, all of it translates into concrete numbers about the universe's composition. It's as if the cosmos took the very thing that muddles our earthly observations and repurposed it as a precision instrument. So while both phenomena might bend light, only gravitational lensing bends our understanding of reality. It takes a trick of perception and flips it into a revelation, proving that sometimes the universe's greatest truths hide not behind a veil, but in the warped reflection of one. Quasars are the universe's ultimate powerhouses, supermassive black holes gorging on gas and dust so fiercely they outshine entire galaxies. But when their light passes through a cosmic funhouse mirror created by a massive foreground galaxy, something extraordinary happens. Instead of a single brilliant point, we see multiple copies of the same quasar scattered across the sky like celestial doppelgangers. These aren't just visual quirks, they're time-stamped messages from across the cosmos, each image flickering slightly out of sync because the light took a different path around the gravitational lens. Take the famous double quasar discovered in 1979, two identical blue specks separated by just 6 arcseconds. At first, astronomers thought they'd found a pair of quasars orbiting each other. But the truth was far stranger. It was one quasar, its light split by an unseen galaxy acting as a lens. The images weren't just twins, they were echoes, with one arriving hundreds of days later than the other due to the extra distance its light traveled. This delay wasn't a bug, it was a feature, a cosmic stopwatch that let scientists measure the lensing galaxy's mass and the quasar's distance with unprecedented precision. But the real magic happens when you realize these delays aren't just about distance, they're about the universe's expansion itself. By tracking how the time gap between quasar images changes over decades, astronomers can measure the Hubble constant, the rate at which the cosmos is stretching. It's like watching a rubber band expand by timing how long it takes for ants crawling along it to reach the same point. Different methods for calculating this rate have famously clashed, creating the Hubble tension, and lensed quasars might hold the key to resolving it. Their time delays act as independent checks, free from the assumptions that trip up other techniques. And quasars aren't just cosmic yardsticks, they're black hole laboratories. When lensing magnifies a quasar's flickering glow, it reveals details otherwise lost in the glare. Astronomers have spotted microlensing within these images, where individual stars in the foreground galaxy briefly amplify parts of the quasar's accretion disk. These flashes are like X-rays, exposing the disk structure and even the black hole's spin. In one striking case, a lensed quasar's images flickered in a way that suggested its black hole was warping space so severely, it dragged the entire disk around with it like a whirlpool. What's truly staggering is how these mirages bridge scales. A single lensed quasar connects the physics of a black hole's chaotic dinner plate where gas spirals in at near light speed to the vast geometry of the expanding universe. They let us weigh galaxies we can't see, clock the cosmos' growth, and peer into the engines of the most violent objects in existence. and with new telescopes like Rubin and Webb set to discover thousands more, these cosmic echoes are about to become our loudest voices in decoding the universe's grandest mysteries. The cosmic web isn't just a backdrop, it's the universe's architectural blueprint, a sprawling network of dark matter filaments woven through the cosmos like invisible threads. Picture a spider's web, but on a scale so vast it connects galaxies across billions of light years, guiding them into clusters and superclusters while leaving yawning voids in between. For decades, this structure existed only in supercomputer simulations, a theoretical framework for how gravity might sculpt the universe over eons. But gravitational lensing has turned theory into breathtaking reality, letting us trace the web's ghostly outlines by studying how it warps the light of distant galaxies. Every subtle distortion in a lensed galaxy's shape is a breadcrumb leading back to the cosmic web's hidden mass. When astronomers analyze thousands of these bent images, patterns emerge, delicate strands of dark matter stretching between galaxy clusters, knots where filaments intersect, and vast empty regions where the web's threads thin to near nothingness. It's like watching wind reveal its presence by rustling leaves, except here, the wind is the gravitational pull of invisible matter, and the leaves are entire galaxies swaying in its current. The most stunning confirmation came from projects like the Dark Energy Survey, which mapped the web in 3D by combining lensing data with galaxy positions, exposing a filamentary structure so precise it matched simulations down to the finest details. What's wild is how this web dictates the universe's evolution. Galaxies don't form randomly, they sprout along filaments like dew on a spider's silk, drawn together by dark matter's gravitational tug. The densest knots become galaxy clusters, while the voids between filaments remain eerily empty, cosmic deserts where matter is almost absent. Lensing lets us watch this process in action, catching young galaxies streaming along filaments like cars on a highway, destined to collide and merge in slow-motion crashes that shape their futures. In the Able 2089 cluster, lensing revealed galaxies being funneled into the cluster's core along dark matter tendrils, a cosmic conveyor belt operating over billions of years. But the cosmic web isn't just a relic of the past, it's a dynamic, ever-changing structure. By comparing lensing maps of nearby and distant galaxies, astronomers have caught the web in motion, watching filaments grow thicker as gravity pulls more matter into them, while voids expand like bubbles in rising dough. These observations are rewriting our understanding of cosmic evolution, showing how dark matter's scaffolding doesn't just host galaxies, it actively herds them, determining where stars ignite and black holes awaken. And now, with telescopes like Euclid and Rubin poised to map millions more lensing distortions, we're on the verge of seeing the cosmic web in unprecedented detail. Will we find filaments thinner than predicted, voids larger than simulations allow? Each surprise will force us to rethink how dark matter behaves, or perhaps even hint at new physics lurking in the web's shadowy strands. One thing's certain, the universe's largest structure is no longer hidden. Thanks to gravitational lensing, we're not just imagining the cosmic web, we're touching it. Detecting cosmic mirages is like trying to spot a whisper in a hurricane. The universe floods telescopes with light from billions of galaxies, and only a tiny fraction are actually lensed illusions. The first hurdle, telling the difference between a galaxy that's genuinely twisted into a pretzel shape and one that's merely warped by gravity's invisible hand. Some galaxies naturally look odd, with irregular arms or lopsided cores, while others appear stretched because they're caught in the cosmic funhouse mirror of a foreground cluster. Early surveys relied on sharp-eyed astronomers to pick out these distortions manually, a painstaking process akin to finding a specific grain of sand on a beach. But the real challenge lies in the imperfections of our tools. Even the most advanced telescopes introduce subtle distortions, tiny flaws in their mirrors, the blurring effect of Earth's atmosphere, or the faint glow of cosmic dust. These can mimic lensing effects, creating false positives that send researchers down dead ends. To compensate, scientists deploy deconvolution algorithms, mathematical filters that strip away these artifacts like peeling layers off an onion. The Hubble Space Telescope's images, for example, undergo rigorous cleaning to remove distortions caused by its own optics before lensing analysis begins. Then there's the puzzle of mass distribution. When modeling how a galaxy cluster bends light, astronomers must account not just for the visible stars and gas, but the invisible dark matter shrouding them. Get the mass map wrong, and the predicted lensed images won't match reality. This leads to the infamous mass sheet degeneracy problem. Two radically different mass distributions, one clumpy, one smooth, can produce identical lensing patterns. It's like trying to guess the shape of an iceberg by only seeing how it bends the waves around it. Enter machine learning. Modern surveys like the Dark Energy Survey spew out terabytes of data, far too much for humans to process. Neural networks trained on simulated lenses now scan this deluge, flagging candidates with superhuman speed. But these algorithms aren't flawless. They might miss rare lens types or be fooled by overlapping galaxies. That's why the best systems still pair AI with human oversight, leveraging the pattern recognition of machines and the intuition of seasoned astronomers. Even with these tools, uncertainties linger. Light bending depends on the precise alignment of source, lens, and observer, a cosmic lottery where the odds are never fully known. Some lensed galaxies might be false friends, their distortions amplified by multiple foreground objects acting in concert. Others could be mirages within mirages, their light bent twice by separate clusters. Untangling these layers demands more than computational power. It requires creativity, like using the flicker of a lensed supernova to triangulate the mass of an unseen dwarf galaxy. The future hinges on sharper data. Upcoming telescopes like the Nancy Grace Roman Space Telescope will image lenses with pixel-perfect precision, while radio arrays like the Square Kilometre Array will trace lensing through the warping of hydrogen clouds. Each advance chips away at the noise, bringing the universe's hidden structure into focus. But for now, every cosmic mirage we decode is a testament to human ingenuity, a reminder that the universe's greatest illusions often hide its deepest truths. The idea that cosmic mirages could be windows into parallel universes sounds like pure science fiction, until you consider how much weirder the universe has already proven to be. Among the most tantalizing puzzles in modern cosmology are certain gravitational lensing anomalies that defy conventional explanations. Some galaxy clusters appear to bend light more than their visible mass should allow, while others produce lensed images with peculiar symmetries that don't quite match simulations. Could these glitches be more than measurement errors? A handful of theoretical physicists speculate they might be subtle fingerprints of neighboring universes, their gravity subtly warping ours at the edges of space-time like reflections in a foggy mirror. The math behind this hypothesis stems from string theory's brain-world models, where our universe is a three-dimensional membrane floating in a higher dimensional space, with other brains' parallel universes hovering just out of reach. If these brains wobble or ripple, their gravitational influence might bleed into our cosmos, tweaking how light bends around massive objects. Imagine two bedsheets suspended close together. If one sags, it could subtly tug the other's fabric without them ever touching. That's the essence of the idea. Parallel realities might be nudging our universe's gravity wells in ways that lensing could, in principle, detect. One provocative example is the cold spot, a mysterious void in the cosmic microwave background where temperatures plummet unexpectedly. Some theorists argue it could be an imprint of a collision with another universe, its gravitational shadow subtly distorting lensing patterns in nearby galaxy clusters. Similarly, certain over-lensed quasars whose multiple images appear brighter than predicted have fueled speculation that extra-dimensional gravity is amplifying their light beyond standard models. Skeptics counter that these anomalies likely stem from mundane causes, clumpier dark matter, overlooked galactic mergers, or even telescope calibration quirks. But the mere possibility that lensing could one day test the multiverse theory electrifies the imagination. For now, these ideas remain on the fringe, lacking the smoking gun evidence required to upend mainstream cosmology. Yet history shows that today's wild speculation often becomes tomorrow's textbook fact. Einstein himself initially dismissed gravitational waves as mathematically elegant but physically undetectable until LIGO proved him wrong a century later. Similarly, the hunt for multiverse signatures via lensing is less about proving a specific theory and more about exploring the outer limits of what's measurable. Every unexplained warp in starlight is an invitation to question, to revisit assumptions, and to wonder if the universe's greatest illusion isn't what it hides but how much it's willing to reveal. Whether lensing ever uncovers parallel worlds or not, its true power lies in this relentless boundary pushing, from confirming dark matter's existence to exposing gaps in relativity. Cosmic mirages have repeatedly forced us to rewrite cosmic rulebooks. And if the past is any guide, the next revolution in physics might not come from staring into the void, but from decoding the subtle twists in the light that crosses it. In 1979, astronomers stumbled upon a celestial oddity that would rewrite the rules of astrophysics, the twin quasar, Q0957 plus 561. At first glance, it appeared to be two identical quasars side by side, blazing with the same peculiar spectrum of light, but something didn't add up. The chances of finding two such powerful objects so close together were astronomically slim. The truth, when it came, was far more thrilling. They weren't twins at all, but a single quasar whose light had been split in two by the gravitational pull of an unseen galaxy drifting between it and Earth. This wasn't just a lucky alignment, it was the first confirmed gravitational lens, a cosmic hall of mirrors proving Einstein's once dismissed prediction that mass could bend light like a prism. The twin quasar wasn't merely a curiosity, it became a laboratory. By measuring the time delay between the two images, one path slightly longer than the other, astronomers could weigh the invisible lensing galaxy with unprecedented precision. But the real surprise came when the numbers didn't match. The galaxy's visible stars accounted for only a fraction of the mass needed to create such a stark distortion. The rest, an invisible halo of dark matter, its presence etched into the quasar's warped light like fingerprints on glass. This single discovery didn't just confirm lensing, it handed scientists their first concrete evidence that dark matter wasn't just theoretical. It was real, it was massive, and it was everywhere. Fast forward to 2004, when the Hubble Space Telescope turned its gaze toward Able 1689. A galaxy cluster so massive it warps spacetime like a bowling ball on a trampoline. What Hubble captured wasn't just a cluster, it was a carnival of bent light. Hundreds of background galaxies stretched into luminous arcs and streaks, a mosaic of cosmic mirages painting the cluster's hidden mass in vivid detail. By mapping these distortions, astronomers reconstructed the cluster's dark matter skeleton in 3 dimensions, revealing a spiderweb of invisible filaments connecting galaxies. The images were so precise they exposed individual clumps of dark matter, some no larger than dwarf galaxies, lurking where no stars shone, but the surprises kept coming. When researchers compared lensing maps of Able 1689 with simulations, they noticed something peculiar. The dark matter wasn't just sitting still. It was moving, sloshing around the cluster's core like water in a tilted glass. This wasn't just a snapshot of mass, it was a dynamic portrait of gravity in action, showing how dark matter responds to cosmic collisions over billions of years. Similar observations in the Bullet cluster later caught dark matter red-handed, sailing straight through a galactic wreck while ordinary gas lagged behind. Each of these discoveries hinged on the same principle: light bending where it shouldn't, revealing forces no telescope could see directly. Perhaps the most profound legacy of these cosmic mirages is how they've sharpened our measure of the universe itself. Take the Hubble constant, the rate at which the cosmos expands. For decades, conflicting measurements from supernova and the cosmic microwave background sparked a heated debate. But lensed quasars offered a third way. By tracking the time delays between their multiple images, astronomers could triangulate distances independent of other methods, and the results only deepened the mystery. The numbers still didn't align, hinting at gaps in our understanding of dark energy or even undiscovered physics. From the twin quasars' humble revelation to the sprawling lensed tapestries of modern surveys, these historical cases share a common thread. Every cosmic mirage is a Rosetta Stone waiting to be deciphered. They've confirmed dark matter's grip, exposed the universe's accelerating expansion, and even challenged Einstein's own theories. And with each new lens discovered, we're reminded that the universe's greatest truths often hide not in the light we see, but in the way it bends. Gravitational lensing isn't just a playground for scientists, it's a goldmine for storytellers, a cosmic concept so visually striking and mind-bending that it's leapt from astrophysics journals straight into the heart of popular culture. Take Christopher Nolan's Interstellar, where the black hole gargantua dominates the screen. It's a crescent disk twisted into a luminous halo by the very real physics of light bending. That iconic image wasn't dreamed up in a Hollywood studio. It was painstakingly rendered by a team of physicists running equations to simulate how a spinning black hole would warp starlight. The result, a spectacle so accurate it spawned actual scientific papers, proving that art and science can fuel each other in unexpected ways. But lensing's creative potential goes far beyond visual flair. In Liu Cixin's sci-fi epic The Three-Body Problem, aliens exploit gravitational lensing to amplify their signals across interstellar distances, turning the sun itself into a cosmic magnifying glass. It's a fictional twist rooted in real speculation. Some astronomers have pondered whether advanced civilizations might use lensing effects to communicate, harnessing galaxies as natural telescopes. Even Star Trek has dabbled in the idea, with episodes featuring gravimetric lenses that distort subspace like funhouse mirrors. These stories resonate because they tap into something primal, the thrill of seeing the universe's hidden mechanics repurposed as tools, bridges, or weapons. What's fascinating is how these portrayals walk the line between fact and fantasy. When Contact depicts a wormhole's lensing effect as a shimmering celestial gateway, it's borrowing from real math. Kip Thorne, the Nobel-winning physicist who advised the film, ensured the wormhole's light-bending behavior matched theoretical models. Yet the same film takes creative liberties, compressing decades of interstellar travel into a single jump. That tension between scientific rigor and narrative punch is where the magic happens. Lensing becomes a metaphor for discovery itself, bending the familiar into something wondrous and new. The allure isn't just about spectacle, it's about accessibility. A well-crafted lensing scene can convey complex physics intuitively. In Thor: Ragnarok, the wormhole passage through the devil's anus, yes, really shows space stretching into psychedelic ribbons, a visual shorthand for space-time curvature that's more engaging than any textbook diagram. Even video games like Destiny 2 weave lensing into their lore, with gravity lenses altering weapon trajectories in ways that mirror real light-bending phenomena. These touches matter because they seed curiosity, inviting audiences to ask, could this really happen? And sometimes reality outdoes fiction. When the James Webb Telescope revealed its first deep-field image, packed with lensed galaxies stretched into ethereal arcs, the public reaction mirrored the awe usually reserved for blockbuster CGI. That's the power of cosmic mirages. They blur the line between science and art, proving that the universe's most profound truths often arrive wrapped in breathtaking beauty. Whether it's a black hole's fiery ring on the silver screen or a Hubble photo revealing dark matter's ghostly grip, these moments remind us that the cosmos isn't just stranger than we imagine, it's stranger than we can imagine, until creativity and curiosity light the way. Imagine scrolling through your phone, sipping coffee, and accidentally discovering a cosmic mirage that professional astronomers missed. That's exactly what happened to schoolteacher Hanny Van Arkel in 2007, when she spotted a strange green smudge in a galaxy image while volunteering for Galaxy Zoo, a citizen science project. That smudge turned out to be Hanny's Vorwerp, a never-before-seen quasar light echo, proof that the sharpest tools for spotting cosmic oddities aren't always supercomputers or AI. Sometimes they're human eyes paired with curiosity. This is the magic of projects like space warps, where anyone with an internet connection can sift through telescope images hunting for stretched arcs, rings, and duplicate galaxies, the telltale signs of gravitational lensing. While algorithms excel at processing vast datasets, they often stumble on the unexpected. A lensed galaxy hiding behind a foreground star, or a warped quasar masquerading as camera noise. Human brains, though, are wired for pattern recognition. We instinctively notice asymmetries, subtle curves, or repetitions that machines might dismiss. That's how volunteers have flagged lensed systems like the Eye of Horus, a stunning quadruple-imaged quasar that slipped past automated scans. The impact goes beyond ticking off rare cosmic phenomena. Every new lens catalogued by citizen scientists refines our maps of dark matter, adding data points to models of how mass clusters across the universe. In 2018, Space Warp's participants identified over 300 lens candidates in data from the Subaru telescope, a haul that would have taken professionals years to vet alone. Some discoveries, like a lensed galaxy magnified by a nearby supernova, have even prompted follow-up observations with the James Webb Space Telescope. What's revolutionary isn't just the volume of discoveries, but who's making them. A retiree in Portugal, a high school student in India, and a cafe owner in Brazil have all co-authored scientific papers through these projects, their names listed alongside PhDs. It's a quiet rebellion against the idea that cutting-edge science belongs only to those in lab coats or behind observatory domes. Platforms like Zooniverse, hosting space warps, and dozens of other astronomy projects have turned the hunt for cosmic mirages into a global collaboration, where a single click from a volunteer in Tokyo might reveal a lens that rewrites a footnote in astrophysics. The beauty of this democratization, it's not just about outsourcing labor, it's about rewiring how we perceive discovery. When you spend an afternoon scanning galaxies and stumble upon a gravitational lens, you're not just helping science, you're standing shoulder to shoulder with researchers, peering through the same virtual telescope. That shared gaze, that moment of collective wonder, bridges the gap between ivory towers and kitchen tables, and in a field where the universe's biggest secrets hide in plain sight, sometimes all it takes is a fresh pair of eyes to shift our perspective. While most planet hunting methods rely on catching the shadow of a world crossing its star or measuring a star's subtle wobble, microlensing takes a radically different approach. It lets gravity do the detective work. Picture a lone star drifting through the galaxy, its light traveling undisturbed for thousands of years until, by chance, a planet or another star passes between it and Earth. For days or weeks, the foreground object's gravity warps space like a magnifying glass, bending and amplifying the background star's light into a temporary flare. No direct sighting is needed. The universe itself betrays the hidden object's presence through this telltale brightening. What makes microlensing revolutionary is its ability to spotlight planets other techniques would miss, especially those exiled to the frozen outskirts of their solar systems. While the transit method excels at finding planets hugging their stars tightly, and radial velocity tracks worlds close enough to tug their stars noticeably, microlensing thrives in the cold, dark frontier. It's how astronomers detected an Earth-mass planet orbiting a star 13,000 light-years away, so distant its sun would appear as little more than a pinprick in our sky. Even more astonishing, microlensing can uncover rogue planets, worlds untethered to any star, wandering the galaxy like cosmic nomads. In 2021, a study analyzing microlensing events in our galactic bulge estimated there might be trillions of these free-floating worlds adrift in the Milky Way alone, outnumbering stars 20-1. But the real microlensing marvels are the impossibly distant catches. In 2018, astronomers reported a potential planet in the Whirlpool galaxy, a staggering 28 million light-years away. The signal, a flicker of amplified light, suggested a world orbiting a binary system, far beyond the reach of any other detection method. Though confirming such extremes is fiendishly difficult, the mere possibility hints at microlensing's power to map planets across cosmic distances, turning the entire universe into a hunting ground. The technique isn't without quirks. Each microlensing event is a one-time cosmic alignment, never to repeat. Miss the observation window, and the planet vanishes back into obscurity. Yet this fleeting nature also makes microlensing a democratic tool. It doesn't favor bright, nearby stars but works equally well for faint objects across the galaxy. Projects like OGLE and MOA scan millions of stars nightly, catching these ephemeral flares, while future missions like the Nancy Grace Roman Space Telescope will turbocharge the search, potentially spotting thousands of new worlds, including icy, super-Earths and gas giants in orbits mirroring our solar system's outer realms. Perhaps microlensing's greatest gift is how it reshapes our understanding of planetary systems. By revealing planets at all distances, from scorched inner worlds to frozen outliers, it paints a fuller portrait of galactic diversity. Some systems host cold Jupiters far from their stars, while others fling planets into the void entirely. Each detection is a puzzle piece, showing that the universe crafts planets in ways we're only beginning to glimpse. And as telescopes grow sharper, microlensing promises to expose even more secrets, perhaps twin Earths in distant orbits or moons circling rogue planets, their surfaces warmed not by starlight but by tidal forces. In the grand hunt for other worlds, microlensing isn't just a tool, it's a reminder that sometimes to find what's hidden, you need to watch how the light bends. At the heart of every cosmic mirage lies a mathematical ballet, a delicate interplay between mass, light, and the very fabric of space-time. Einstein's field equations, those elegant yet formidable expressions that link matter to the curvature of space, form the foundation of this dance. To predict how a distant galaxy's light will warp around a foreground cluster, physicists must solve these equations, tracing how every ounce of mass, visible or dark, twists the cosmic stage beneath it. But here's the catch. Solving these equations in full glory for a real galaxy cluster is like calculating the airflow over every ridge of a mountain range while blindfolded. The sheer complexity demands shortcuts, and that's where the thin lens approximation comes in. This clever simplification treats massive objects as two-dimensional sheets, as if you could flatten a galaxy cluster into a pane of glass suspended in space. Light passing through this pane bends at precise angles, determined by the sheet's density at each point. It's a bit like how a magnifying glass focuses sunlight, except instead of glass, the lens is made of pure gravity. This approximation strips away layers of complexity, allowing astronomers to model lensing effects without drowning in calculations. But even with this simplification, the math is far from trivial. The thin lens approach still requires mapping the mass distribution of the cluster where the dark matter clumps, how the galaxies are arranged, and then solving for how that particular configuration distorts light from behind. Enter supercomputers, the unsung heroes of modern lensing science. These machines churn through billions of calculations, testing countless mass distributions until the simulated lens matches the warped galaxies we observe in telescope images. It's a cosmic game of trial and error, where each iteration tweaks the invisible scaffolding of dark matter, nudging it until the virtual arcs and rings align with reality. Projects like the Millennium Simulation have spent millions of processor hours recreating the universe in silico, generating synthetic skies where every lensed galaxy is a benchmark for testing our theories. What's astonishing is how this math bridges scales. The same equations that describe a black hole's crushing grip also govern the gentle bending of light around a modest galaxy. And when observations deviate from predictions, when a lensed image is slightly brighter or more distorted than the models expect, it's often a signpost to new physics. Perhaps dark matter interacts with itself in unexpected ways, or maybe gravity itself behaves differently on cosmic scales. The numbers don't lie, they whisper where our theories might need revision. This convergence of theory and observation is what makes lensing so powerful. It turns abstract equations into a forensic tool, letting us weigh galaxies we can't see and map voids we'd otherwise overlook. From Einstein's scribbled notes to the pixel-perfect simulations of today, the mathematics behind lensing isn't just about solving puzzles. It's about translating the universe's hidden language into something we can finally understand. Science thrives on skepticism, and gravitational lensing is no exception. While cosmic mirages have revolutionized astronomy, not every warped galaxy or strange arc turns out to be the real deal. Take the case of huge LQG, a proposed superstructure of quasars that initially appeared aligned in a way suggesting lensing by an unseen mass. Further analysis revealed it was likely just a chance grouping, a cosmic coincidence that fooled even seasoned researchers. Then there's the Hoag's object controversy, where a stunning ring galaxy was briefly theorized to be an extreme lensing effect before observations confirmed its structure was intrinsic, not a trick of gravity. These missteps aren't failures, they're the scientific process in action, a reminder that nature often mimics its own illusions. The debates get even thornier when lensing observations seem to clash with Einstein's general relativity. In the Bullet cluster, for instance, the separation of dark matter from visible gas fits standard models perfectly. But other clusters, like Able 520, show lensing patterns that some argue require modified gravity theories, alternatives to dark matter where gravity itself behaves differently at large scales. Proponents point to subtle anomalies in how light bends around these clusters, suggesting invisible mass might not be the only explanation. critics counter that imperfect data or overlooked astrophysical processes could account for the discrepancies. It's a high-stakes tug of war, with each new lensing map either shoring up Einstein's legacy or chipping away at it. What keeps these controversies productive is the relentless drive for better tools. Early lensing surveys relied on crude mass models, leading to false positives. Today, machine learning algorithms cross-check potential lenses against millions of simulated scenarios, flagging oddities for human review. Projects like the Legacy Survey of Space and Time will soon deliver such pristine data that even minor deviations from theory, say, a lensed quasar image a fraction too bright, could signal new physics. The most heated debates often birth the most ingenious methods, like using time delays between lensed supernova images to measure the Hubble constant independently of other techniques. At its core, these disputes reveal something profound. Cosmic mirages aren't just answers, they're questions etched in light, challenging us to look deeper. Whether confirming dark matter's existence or hinting at gravity's unresolved quirks, each contested observation pushes astronomy closer to a fuller picture of the cosmos, one bent, magnified, and reflected through the universe's own distorted lens. Peering through a gravitational lens is like unlocking a time capsule from the universe's earliest chapters, one that holds snapshots of cosmic dawn, when the first stars flickered to life in the darkness. Among the most astonishing discoveries are lensed galaxies like GNZ 11, whose light began its journey just 400 million years after the Big Bang. Normally, such distant objects would be too faint to study in detail, but the magnifying effect of a foreground galaxy cluster stretches their glow, transforming faint whispers into vivid postcards from the infancy of creation. These aren't just ancient relics, they're laboratories for testing how the cosmos transitioned from a featureless sea of gas to a tapestry of galaxies. Take the Sparkler Galaxy, a lensed gem spotted by the James Webb Space Telescope. Its distorted image reveals clusters of stars so pristine, they're virtually untouched by the pollution of heavier elements, a chemical fingerprint proving they formed from the primordial hydrogen and helium left by the Big Bang itself. By counting these star clusters and measuring their sizes, astronomers have confronted a puzzle. Some appear too massive and mature for their age, challenging assumptions about how quickly structure emerged in the early universe. It's like finding a fully grown tree in what should be a field of saplings, forcing us to rethink the timeline of cosmic evolution. These observations don't just test theories, they rewrite them. Simulations of the early universe running on supercomputers predict that the first galaxies should be small and ragged, slowly merging over billions of years. Yet lensed galaxies like EGSI 8P7, magnified by foreground clusters, show pockets of intense star formation and intricate structures far earlier than expected. Some even host supermassive black holes that, by all rights, shouldn't have had time to grow so large. The discrepancy has sparked a cosmic detective story, with scientists scrambling to adjust models of dark matter's behavior or the role of mysterious phenomena like primordial black holes in seeding rapid growth. What's truly groundbreaking is how lensing exposes the universe's baby photos in motion. In one remarkable case, a lensed galaxy from just 500 million years after the Big Bang shows streams of gas being siphoned into its core, the very fuel for star formation caught in the act. Another reveals bubbles carved by the violent deaths of early stars, their explosions scattering the heavy elements that would later seed planets and life. These aren't static snapshots, they're frames in a cosmic film strip showing the universe's first steps toward complexity, yet the biggest revelations may still lie ahead. Upcoming telescopes like the Nancy Grace Roman Space Telescope, aim to discover thousands more of these lensed primordial galaxies, building a statistical atlas of the cosmic dawn. Will they confirm the outliers we've seen so far, or reveal an entirely new population that upends our theories? Every warped image from the early universe is a vote in the grand ballot of cosmology, and gravitational lensing is the tool letting us count them. By bridging 13 billion years of history, these cosmic mirages don't just show us where we came from, they hint at how much we've yet to learn. Gravitational lensing might seem like a tool reserved for probing distant galaxies, but its influence stretches far beyond pure astronomy, reaching into technologies we use every day. Take GPS navigation, for example. Without accounting for relativity's subtle effects, including how Earth's gravity slightly warps spacetime, your phone's map would drift off course by roughly 10 kilometers per day. The math behind these corrections borrows from the same principles that predict how massive objects bend light, fine-tuning satellite signals with precision that keeps delivery drivers, hikers, and even missile systems on target. It's a quiet revolution. Einstein's abstract equations, tested by cosmic mirages, now live in your pocket, the next frontier, turning the universe itself into a telescope. Imagine using the sun's gravity as a colossal lens, focusing light from distant exoplanets into a detectable signal. NASA's proposed Solar Gravitational Lens mission aims to do just that, parking a spacecraft nearly 900 times farther from the sun than Earth to exploit this natural magnification. At that distant point, light from an alien world would bend around the sun's edges, forming a ring of fire that a telescope could stitch into a high-resolution image. Instead of guessing at an exoplanet's surface features through indirect methods, we might one day map its continents, oceans, and even city lights, all thanks to the same physics that creates Einstein rings in deep space. Even art historians are borrowing tricks from lensing science. When conservators analyze Renaissance paintings for forgery, they sometimes use techniques inspired by gravitational lens mapping. By studying how light scatters through layers of varnish and paint, a process mathematically akin to tracing light through a cosmic lens, they can detect inconsistencies invisible to the naked eye. A brushstroke that refracts light too perfectly might reveal modern pigments masquerading as centuries-old oils, unmasking fakes with astrophysical precision. These spin-offs share a common thread. The most abstract discoveries often ripple outward in unexpected ways, from keeping your road trip on course to unmasking a counterfeit Van Gogh. Lensing proves that the universe's grandest illusions don't just reshape our view of the cosmos, they refine how we navigate, explore, and even preserve our own world. And as technology advances, the line between celestial phenomena and earthly innovation will only blur further, turning today's cosmic curiosities into tomorrow's indispensable tools. Gravitational lensing may be the universe's most elegant trick, but even magic has its limits. Like a spotlight in a vast theater, it illuminates only certain corners of the cosmos' massive galaxy clusters, distant quasars, and the occasional star perfectly aligned with a black hole. Smaller objects like rogue planets or dim dwarf galaxies often slip through the cracks. Their gravity is simply too weak to bend light noticeably, leaving them invisible to even the most sensitive lensing surveys. And while lensing excels at probing the distant universe, it struggles with objects close to home. A nearby star or exoplanet would need to pass almost perfectly in front of a background star to create a detectable microlensing event, a cosmic alignment so precise it's like threading a needle across light years. Then there's the cosmic clutter. Dust clouds within galaxies or even within our own Milky Way can smudge lensed images like fingerprints on a camera lens. In extreme cases, they absorb the very light lensing relies on, rendering distant galaxies invisible. Even when light does make it through, overlapping lenses multiple galaxies or clusters bending light along the same line of sight can twist signals into chaotic knots. Imagine trying to decipher a message written on a funhouse mirror, only to find someone has stacked 3 more mirrors in front of it. The result, a hall of mirrors effect where astronomers must untangle which distortions come from which mass, a puzzle that can take years to solve. These limitations aren't just technical hurdles, they shape what we can and can't learn. Lensing maps dark matter's broad strokes but misses its fine details, like the predicted swarms of tiny dark matter clumps orbiting galaxies. Simulations suggest these mini halos should exist, but they're too small to lens light detectably, leaving a gap in our understanding of how dark matter behaves on the smallest scales. Similarly, lensing can't peer into the hearts of black holes or resolve the surfaces of distant exoplanets, tasks requiring other tools, like radio telescopes or direct imaging. Yet the future is bright. Next-generation observatories like the Vera C. Rubin Observatory will scan the sky with such speed and precision that they'll catch fleeting lensing events others miss, while the James Webb Space Telescope's infrared eyes pierce through dust that stymies optical surveys. Even more promising are hybrid approaches where lensing data gets fused with other techniques. Combine a lensing map with X-ray observations of hot gas, for instance, and suddenly you're not just weighing a galaxy cluster, you're seeing how its dark matter and visible matter interact. The lesson here isn't that lensing falls short. It's that the universe demands a symphony of methods, each instrument playing its part. Lensing reveals the invisible mass, spectroscopy deciphers chemical compositions, and gravitational wave detectors listen for the ripples of colliding black holes. Together, they're not just filling gaps, they're rewriting the score of cosmic discovery, proving that even the universe's grandest illusions make more sense when we view them from every angle. Deep in the heart of every cosmic mirage lies a tantalizing possibility that the warping of light might hold clues to physics' greatest unsolved mystery, how gravity dances with the quantum world. At the scale of galaxies, Einstein's relativity predicts lensing with breathtaking precision. But zoom into the realm of atoms and particles, and the equations falter. Quantum mechanics governs here with its probabilities and uncertainties, while gravity, the force that sculpts the cosmos, refuses to play by the same rules. This schism has haunted physicists for a century, but gravitational lensing might offer a backdoor to reconciliation. Imagine if the universe's most dramatic light-bending effects weren't just cosmic curiosities, but magnifying glasses trained on spacetime's finest grains. One audacious idea involves primordial black holes, hypothetical relics from the universe's first moments, some no larger than a proton. If these minuscule monsters exist, their gravity could lens light in bizarre ways, imprinting telltale flickers or split images on distant starlight. Unlike their stellar-sized cousins, these quantum-scale black holes wouldn't bend light smoothly. Instead, their lensing might reveal a pixelated spacetime, flickering as if projected through a cosmic mesh screen, a signature that gravity, at its core, is quantized. Projects like the Subaru Telescope's HSC survey are already scouring the sky for such anomalies, hunting for stars that brighten or warp in ways no classical black hole could explain. Even wilder are proposals involving exotic matter particles that defy known physics, like theoretical topological defects left over from the Big Bang. These cosmic wrinkles, if real, could lens light in ways that expose spacetime's underlying quantum fabric. Picture a distant quasar whose light doesn't just bend around a galaxy, but shimmers with interference patterns as if passing through a subatomic sieve. Such observations would suggest that spacetime isn't the smooth continuum Einstein envisioned, but a frothing quantum foam at microscopic scales, with lensing acting as our only microscope. The challenge: these quantum gravity signatures would be vanishingly faint, buried in noise from cosmic rays, atmospheric distortion, and instrument limits. Detecting them requires telescopes of unprecedented sensitivity, like the upcoming square-kilometer array, whose radio eyes could spot subtle lensing distortions in the faint whispers of hydrogen atoms. Others propose space-based interferometers, combining multiple satellites to measure starlight's path with picometer precision, sensitive enough to catch spacetime's hypothetical granularity, warping light over interstellar distances. What makes this frontier thrilling isn't just the potential discoveries, it's the philosophy. If lensing can expose quantum gravity's fingerprints, it means the universe's grandest illusions are intimately tied to its smallest building blocks. A single photon's detour around a galaxy might carry whispers of Planck-scale physics, bridging the vast gulf between cosmic and quantum realms. From the warped starlight of distant quasars to the subatomic shivers of spacetime itself, gravitational lensing isn't just mapping the universe's hidden mass, it's probing the very rules that make reality possible. And in that delicate interplay, we might finally find the missing link between the force that binds stars and the glue that holds atoms together. Astronomy has always been a universal human endeavor, from the earliest stargazers tracking celestial patterns to modern telescopes peering into deep space. Yet as gravitational lensing surveys expand, scanning billions of galaxies across indigenous lands and remote observatory sites, they're forcing a reckoning with questions that transcend pure science. Take the proposed 30-meter telescope on Mauna Kea, Hawaii. While its lenses could revolutionize our view of cosmic mirages, its construction on land sacred to native Hawaiians sparked protests that halted progress for years. This tension isn't unique. In Chile's Atacama Desert, where the skies are so clear they've become a hub for lensing research, local communities wrestle with the environmental and cultural impacts of sprawling telescope arrays. The irony is profound: the same tools revealing the universe's hidden structures sometimes overlook the earthly ecosystems and traditions they're built upon. Data ownership adds another layer of complexity. When a lensing survey captures a distant Einstein ring, who does that discovery truly belong to? The scientists who analyzed it, the funding agencies that paid for the telescope, or the indigenous peoples whose ancestors first mapped the night sky with stories now echoed in those very distortions? Projects like the Sloan Digital Sky Survey have pioneered open data policies, sharing lensing maps with researchers worldwide. But this openness rarely extends to the communities living beneath the telescopes, many of whom lack the infrastructure to participate in the research their landscapes enable. It's a disparity that mirrors the broader inequities in astronomy, where a handful of wealthy nations dominate access to cutting-edge tools while regions with pristine skies often watch from the sideline. The solution isn't abandoning progress but reimagining collaboration. In Australia, the Square Kilometre Array project partnered with Wajiri Yamaji elders to ensure the telescope's placement respected sacred sites, blending traditional knowledge with astrophysical goals. Similarly, the Mauna Kea Spectroscopic Explorer now includes Hawaiian cultural advisors in its planning, recognizing that the mountain's significance isn't just atmospheric but spiritual. These models show how science can thrive without silencing other ways of knowing, whether it's incorporating indigenous star lore into lensing research or training local communities to operate the very instruments scanning their skies. At its core, this ethical shift acknowledges that the universe isn't just something we observe, it's something we experience together. When a gravitational lens reveals a galaxy from the cosmic dawn, that light belongs as much to the descendants of the first astronomers as it does to the institutions that captured it. By weaving cultural stewardship into the fabric of discovery, we don't just expand our view of the cosmos, we honor the countless eyes that have gazed upward long before telescopes existed, and the countless voices still waiting to join the conversation. The greatest cosmic mirage of all might be the illusion that science and ethics orbit separate skies. Long before telescopes and equations, the night sky was a canvas for human stories, a place where light and shadow weren't just observed but woven into the fabric of culture. For the Maori of Aotearoa, the Milky Way isn't merely a band of stars. It's Te Ikaroa, the great fish of the sky, whose celestial currents guide voyagers across oceans. When a star appears to flicker or shift, Maori astronomers speak of Tatai Arorangi, the Matariki, a celestial dance where such changes signal seasonal shifts or ancestral messages. In this worldview, a distorted star isn't just a lensing effect. It's a whisper from the past, a reminder that the cosmos communicates in ways beyond data. Across the sea, Aboriginal Australian traditions describe the emu in the sky, a dark silhouette carved by the dust lanes of the Milky Way. To the Wardaman people, certain stars are Nadi, or cosmic firesticks, whose movements and brightness variations, some aligning with microlensing events, mark sacred ceremonies or herald the arrival of monsoon rains. These interpretations don't contradict astrophysics. They expand it, framing light's journey as a narrative threaded with ecological and spiritual meaning. Where Western science sees a quasar's bent light as evidence of dark matter, Aboriginal elders might recognize it as the footprints of creation ancestors, mapping the land of the sky. These perspectives aren't folklore to be sidelined, they're parallel ways of knowing, refined over millennia of observation. Take the Navajo concept of Nilchi, the wind that breathes life into the universe. In their cosmology, celestial distortions aren't just gravitational quirks. They're the breath of the cosmos itself, shaping reality as it flows. Compare this to the modern understanding of space-time curvature, and the parallels are striking. Both describe an invisible force molding the visible world, one through metaphor, the other through mathematics. The beauty lies in the dialogue. When astronomers discovered a lensed galaxy cluster in the Southern Cross, a constellation central to many Pacific navigational traditions, they collaborated with Maori scholars to name it Pohutukawa, after the crimson blossom tree symbolizing connections between Earth and sky. The cluster's warped galaxies, magnifying light from the early universe, became a shared metaphor. Just as the tree's roots and branches intertwine, so too do indigenous knowledge and astrophysics, each grounding the other in deeper understanding. This isn't about choosing one truth over another. It's about recognizing that cosmic mirages, like all great mysteries, defy a single interpretation. To a physicist, a lensed quasar is a laboratory for testing relativity. To a Polynesian wayfinder, it might be a beacon confirming a star path's accuracy. Both are valid, both are vital, and together, they remind us that the universe's grandest illusions aren't just puzzles to solve. They are invitations to listen, to learn, and to see the sky not just as it is, but as it's been imagined, measured, and revered across the tapestry of human thought. You don't need a billion-dollar telescope to bend light like the cosmos does, just a wine glass, a flashlight, and a dash of curiosity. Picture this: shine a laser pointer through the curved base of a glass, and suddenly, the beam doesn't just pass through, it fans out into a shimmering arc, a tiny echo of how galaxies warp starlight across the universe. This simple trick isn't just a party experiment. It's a gateway to understanding relativity with nothing more than household items. The glass's curvature acts like a gravitational well, refracting light just as a black hole or galaxy cluster would, proving that the universe's grandest illusions obey rules we can recreate on our kitchen tables. Science educators have taken this idea even further, using water droplets as miniature cosmic lenses. Suspend a drop of water on a wire, project a grid pattern behind it, and watch as the lines distort into elegant curves, a direct parallel to how foreground galaxies twist the shapes of background stars in telescope images. These demos strip away the complexity of equations, letting students see spacetime's curvature in action. One teacher in Minnesota even rigged a fish tank with sugar solutions of varying densities to simulate how light bends through uneven gravitational fields, creating a tangible model of Einstein's happy thought about falling elevators and bent light beams. The real magic happens when kids realize they're not just playing with light, they're touching the same forces that sculpt the cosmos. High school clubs have built Einstein ring generators, using old projector lenses and smartphone cameras, capturing their own tiny versions of the celestial halos Hubble spots in deep space. Others use smartphone apps to track how mock quasar LEDs appear to shift position when viewed through a warped acrylic sheet, mirroring the way real quasars' images dance around massive galaxies. These projects don't just teach physics, they spark the kind of awe that turns casual observers into lifelong explorers. What's revolutionary about these experiments isn't their simplicity, it's their accessibility. A student in Nairobi or Quito can grasp dark matter's gravitational grip by stretching a rubber sheet with marbles, watching heavier ones sink deeper and bend, passing laser beams more sharply. No supercomputers, no jargon, just hands-on proof that mass warps space and warped space guides light. When a 12-year-old twists a spoon in a glass of water and gasps as the handle breaks at the surface, they're not just seeing refraction. They're witnessing the same principle that lets astronomers weigh invisible galaxies millions of light years away. The best part, these demos are just the start. Amateur astronomers now collaborate with universities, analyzing real lensing data from projects like Zooniverse's space warps to spot cosmic mirages professionals might have missed. Who knows, maybe the next great lensed galaxy discovery won't come from a PhD's analysis, but from a teenager tinkering with a water droplet and a dream, realizing that the universe's secrets aren't locked away in distant space. They're right here, waiting to be uncovered with a little creativity and a lot of wonder. Every observation we make about the universe comes with an unspoken assumption that light travels in straight lines, faithfully delivering truth from the cosmos to our eyes. But gravitational lensing shatters that simplicity, forcing us to confront a far stranger reality. The universe isn't just showing us distant objects, it's actively editing the footage, warping and rearranging starlight like a cosmic film director splicing scenes out of order. This revelation isn't just about astronomy, it's a philosophical earthquake that rattles the foundations of how we perceive existence itself. Consider the ancient allegory of Plato's cave, where prisoners mistake shadows on a wall for reality. Gravitational lensing presents us with a modern version of this dilemma. When we see multiple images of the same quasar or a galaxy stretched into a glowing arc, we're not witnessing the object as it truly is, but as gravity has manipulated it. The light arriving at our telescopes has been bent, delayed, and magnified sometimes by multiple lenses in succession, creating a version of reality that's been filtered through spacetime's funhouse mirrors. This raises an unsettling question. If even the most objective tools of science can't deliver raw, unfiltered truth, how much of our cosmic understanding is built on distorted foundations? Scientists have developed ingenious workarounds, using supercomputers to reverse engineer lensed images back to their original forms. It's like listening to a song played through a series of echoing halls and trying to reconstruct the original melody by accounting for every bounce. But this process relies on assumptions that we understand gravity's rules perfectly, that dark matter behaves predictably, that no unknown physics lurks in the gaps. Each lensed galaxy becomes a test of these assumptions, and sometimes the universe throws curveballs, certain lensing anomalies, like the impossible brightness of some lensed supernova or odd symmetries in Einstein rings, hint that our models might be incomplete, that spacetime's editing software contains bugs we haven't discovered yet. This uncertainty mirrors debates in quantum mechanics, where the act of observation alters the observed. In lensing, we don't change the universe by looking, but the universe changes what we see before we even look. Some philosophers argue this makes lensing the ultimate metaphor for scientific humility. No matter how advanced our tools, we're always interpreting reality through layers of distortion, both literal and cognitive. The cosmic mirage becomes a reminder that objectivity might be an illusion, that every observation is a collaboration between the universe's tricks and our attempts to decode them. Yet there's profound beauty in this limitation. Just as Cubist paintings revealed multiple perspectives simultaneously, lensed images show us galaxies from several angles at once, nature's own multidimensional artwork. A single Hubble image might contain a distant galaxy's light from 3 different epochs, arriving via separate paths around a lensing cluster. We're not just seeing the universe, we're seeing it refracted through the prism of relativity, offering glimpses of reality that flat, undistorted views could never provide. Perhaps truth isn't about stripping away distortions, but learning to read them, to see the universe not as it is, but as it interacts with itself, with gravity as both artist and interpreter. At its core, gravitational lensing does more than reveal hidden mass or magnify distant galaxies. It holds up a mirror to the human quest for understanding. Every warped image challenges us to ask, when the cosmos conspires to deceive, is it hiding reality or revealing a deeper one? The answer might lie not in choosing between the distorted and the true, but in embracing the realization that in a relativistic universe, distortion isn't error, it's information. And learning to decode that information may be the most important scientific and philosophical journey of all. Lensing doesn't just reveal the universe's hidden architecture, it might also hold the key to answering humanity's oldest question: are we alone? Imagine an alien civilization far beyond our technological grasp, deliberately bending starlight to send signals across the cosmos. Just as gravity distorts distant galaxies, it could also twist artificial transmissions, radio waves, or laser pulses into recognizable patterns. Scientists in the SETI program have begun considering this wild possibility, scouring lensed signals for unnatural repetitions or geometric precision that nature alone couldn't produce. It's a cosmic game of telephone where the universe's own distortions might carry messages we've only dreamed of decoding. The concept isn't as far-fetched as it sounds. Advanced civilizations, if they exist, would face the same challenge we do, the mind-numbing vastness of space, but gravitational lensing offers a loophole. A species could use a star or black hole as a natural amplifier, focusing their signals like an interstellar lighthouse. Picture a beacon aimed at a distant galaxy cluster, knowing its gravity would stretch and magnify the transmission across thousands of light years. For us, detecting such a signal would be like finding a deliberate ripple in a sea of cosmic static, a signature too precise to be accidental. Some theorists take this idea even further, proposing that alien astronomers might already be using lensing to study us. A sufficiently advanced civilization could position telescopes at the focal points of our sun's gravitational lens, turning it into the ultimate spyglass. From their vantage, Earth's pale blue dot would resolve into continents and city lights, our broadcasts amplified by the sun's curvature, the unsettling implication. We might be under observation without ever knowing it, our planet's image captured by lenses we didn't build, echoing across the galaxy like a reflection in a mirror we can't see. Of course, skepticism is healthy. The universe is full of natural oddities, pulsars that tick like clocks, quasars that flicker with eerie regularity, so distinguishing an alien signal from cosmic noise remains daunting. Yet the search pushes technology forward. Projects like Breakthrough Listen now analyze lensed radio waves for narrowband frequencies or repeating structures that defy astrophysical explanations. Others hunt for laser pulses that, when bent by gravity, might arrive in telltale bursts of synchronized photons. Even if the odds are slim, the payoff would rewrite history, proof that the universe's greatest illusion isn't just revealing hidden mass but hidden neighbors. The beauty of this hunt lies in its duality. Whether we find intelligence or silence, lensing forces us to confront our place in the cosmos. Each distorted signal we decode, whether natural or engineered, adds another piece to the puzzle of whether life is a fluke or a cosmic inevitability. And if one day, amid the warped whispers of distant starlight, we catch a pattern too perfect to ignore, it won't just answer a question. It'll remind us that the universe's grandest trick might be hiding its inhabitants in plain sight, waiting for the right moment and the right lens to reveal them. From bending starlight to mapping dark matter, cosmic mirages have reshaped our understanding of the cosmos in ways Einstein himself might never have predicted. These gravitational illusions started as curiosities, strange smudges on photographic plates, unexplained duplicates of distant quasars, but today they've become astronomy's most versatile tools, revealing the invisible scaffolding of the universe itself. Every warped galaxy, every stretched arc of light, is a testament to how profoundly interconnected reality truly is, with mass and energy dictating not just where objects are, but how we see them. What's most astonishing isn't just what lensing has shown us, but how it's humbled us. For centuries, we assumed light traveled in straight lines, carrying undistorted truths across the void. Now we know better. The universe is no passive stage. It's an active participant, twisting and magnifying starlight like a cosmic editor, forcing us to question every observation. When Hubble captures a ring of light 9 billion light-years away, we're not just seeing a galaxy, we're seeing spacetime's craftsmanship, a reminder that even the laws of physics can sculpt illusions breathtaking enough to fool us. Yet these illusions are anything but deceitful. They're guideposts pointing to deeper truths. Without lensing, dark matter would still be a shaky hypothesis, dark energy a speculative footnote. Without those early twin quasars, we might never have grasped how much of the universe hides in plain sight. And now, as next-generation telescopes like Euclid and the Vera C. Rubin Observatory come online, we're poised to uncover even more. Will we find lensed supernova that crack the mystery of the universe's expansion rate? Could subtle anomalies in Einstein rings hint at extra dimensions or quantum gravity? The questions outnumber the answers, and that's exhilarating. So the next time you look up at the night sky, remember, some of those twinkling lights aren't where they appear to be. A flicker might be a star magnified by a black hole's gravity. A faint smudge could be a galaxy stretched across billions of years. The cosmos isn't just showing us its wonders, it's hiding them in the bends and warps of spacetime, inviting us to look closer, think deeper, and embrace the beautiful irony that sometimes, to see the universe clearly, we first have to decode its illusions.